Okay. So this is our packet for hypothesis testing part 2. We're going to start off with just kind of a little more theory about our hypothesis testing, some cautions about our significance. So for our first example, 2 separate scientists conducted a study to determine if a new diet helps reduce weight. So same new diet. They both chose a significance level of 0.05. Now George found a p-value of 0.0503. So should he fail to reject, or reject the null hypothesis that the diet does not reduce weight? So 0.0503, is that a big or small p-value? That is bigger than alpha, so it is a big p-value. So he will reject the null hypothesis. Okay, because what that means is that if the null hypothesis of the diet doesn't help reduce weight, the probability that he found his sample results or something more extreme was only 5.03%. Now Dan found a p-value of 0.0498. Should he reject or fail to reject the null hypothesis? So 0.0498, is that bigger or smaller than 0.05? That is okay, big p-value means fail to reject. Now, Dan has a small p-value, which means that he does get to reject the null hypothesis. Okay. So George, the probability of him finding his sample results or something more extreme, if the diet really doesn't do anything, is 5.03%. Now Dan, the probability of him getting his results or something more extreme, if the diet really doesn't do anything, is only 4.98%. Okay. So did they come to different conclusions? Definitely yes, different conclusions. Okay. But I mean, what's the difference between 5.03% probability and 4.98% probability of getting your test statistic or something more extreme if the null hypothesis were true? Okay. It doesn't seem like those p-values were very different. Okay, and remember that a small p-value indicates strong evidence against the null hypothesis. So how does the strength of evidence compare for the 2 scientists? So one has a p-value of 0.0503, one has a p-value of 0.0498. So shouldn't the strength of that evidence be fairly similar for those 2 people? It should be pretty close. So what happened here? It was just the fact that ahead of time we set our defining rule. We say if it's smaller than alpha, we'll reject. Bigger than it, we will fail to reject. So even if you are close, you set your rule in advance and you have to stick to it. Okay? But that is one reason that we report our p-value and not just our conclusion, because we want to tell them how much evidence we actually found. And so for our next example, Jillian also conducted a weight loss study for a diet she created. She wants to know if participants will lose weight on her diet. She measured the average weight loss of her participants over 6 months. The null hypothesis is that on average there was no weight loss. Jillian found her sample of 30 people lost an average of 0.3 pounds over the 6 months. Remember it's positive values because we're measuring actual weight loss. She conducted a hypothesis test and found a p-value of 0.0000, a few O's in there, 3.1. Okay. She rejects the null hypothesis and concludes that she has very, very strong evidence that her diet, the participants on her diet are going to lose weight. Okay. Because that p-value is so small that she has extremely, extremely strong evidence that they lost weight. Okay. So are her results statistically significant? Yes, because p-value is less than alpha. Now, they didn't tell us a specific alpha, but for any alpha you choose, that p-value is going to be smaller than it. So that's how you tell statistically significant. Statistically significant is anytime you have small p-values. So she is very, very sure that her participants lose weight. Okay. Now, what about are her results practically significant? So this means, would you as a consumer care to go try her product? Okay, why not?
She only lost on average of 0.3 pounds. You lose that by not eating lean.
Okay. No, so only an average of 0.3 pounds over 6 months. Okay, so again, we're very sure that they did lose weight, but you might have to go ask the study, well, how much weight did they actually lose? Not just that we're sure they lost weight, but is that weight difference enough to actually take the diet? Does that make sense? Okay, so that's our difference between statistically significant and practically significant. So for this one, John and Matt have never met or talked. Coincidentally, they both conducted a study to see if the mean breaking strength of a new material is less than 40 pounds. Assume the population standard deviation is 0.3 pounds. John took a sample size of 30 bags and found a sample mean of 39.95. Amazingly enough, Matt also found a sample mean of 39.95. However, he used a sample of 1,000 bags. So let's go through and just compare things. So they both have the same sample mean, same population standard deviation. The only thing that's different is their sample size. John has 30, Matt has 1,000. Okay. Now when I find my test statistics, so I plug the numbers in, so mean, sample mean minus hypothesized mean over population standard deviation over the square root of n. John gets a test statistic of negative 0.91. Matt gets a test statistic of negative 5.27. Okay, now this means that John gets a p-value of 0.1807. Okay. Now they didn't tell me a significance level, so let's pick one. What should we pick? If you don't have a good reason to use something else, use 0.05. So at alpha equals 0.05, should John reject or fail to reject the null hypothesis? Is that a big or small p-value? It is a big p-value. Okay, which means that he will fail to reject. Okay, so if he fails to reject the null hypothesis, or he gets a big p-value, then that means that it is not statistically significant. Okay, so we have no reason to believe that, well, let's see, if we set this up, the null hypothesis and alternative hypothesis, the alternative is they want to know if it's less than 40. So the null hypothesis would be that it is 40. Okay. So we didn't reject the null hypothesis, so we have no reason to believe that it's not, that it is less than 40. So no reason to believe that it is less than 40. Now Matt, because he had n equals 1,000, he got a test statistic really far out on the tail, and his p-value is really, really, really small. So this is a small p-value, and he will reject it. So his results are statistically significant. So what happened here? All we did was change the sample size. So what we figured out here is that when you change the sample size, even small differences, so going from 39.95 from 40 to 39.95, so I mean that breaking strength is only 0.05 pounds different from your hypothesized mean of 40. Okay, so even a very small difference, if you make the sample size big enough, it will make even very small differences statistically significant. So Matt, yes, he is very, very sure that that population mean is less than 40, but it's probably only like 0.05 pounds less. Okay. So you have to keep in mind that even though bigger sample sizes, we know that bigger sample sizes give us like more precise confidence intervals, and they always give us like better results. But you have to keep in mind that it's going to give you better statistical results, and it might not necessarily give you better practical results. So you're going to be more likely to get things that are statistically significant but not practically significant. Okay, so our cautions about significance summarized. So this is what we were supposed to learn from all of our examples. So there's no sharp border between significant and not significant. Just increasingly strong evidence as the p-value increases. Or, sorry, as the p-value decreases. So that was our first example where one had a p-value of 0.0503 and one had a p-value of 0.0498. So their strength of evidence was almost exactly the same, but one of them got to reject and one of them didn't reject. And so you just have to keep in mind that the p-value really matters more than your conclusion. Okay, which is why we always want to report our p-values. Okay, remember statistical significance is different from practical significance, and very small effects can be highly significant, okay, which is when you get a small p-value, if you have a large enough sample size. And finally, this one wasn't pointed out here, but you need to remember it, is the lack of significance. So when you fail to reject, doesn't imply that the null hypothesis is true, just that we didn't find any evidence against it, or we didn't find sufficient evidence against it. So we're going to talk about some errors some more. We talked about them on the first day. So we have type 1 errors, type 2 errors, and then we're going to learn about something called power. So remember, a type 1 error is when you reject a true null hypothesis, and a type 2 error is when you fail to reject a false null hypothesis. So you can summarize it in a diagram like this. So you have your state of nature, or the truth, is that the null hypothesis is true, or that the null hypothesis is false. And then you have to make a decision. So if you have a true null hypothesis and you fail to reject it, that was your correct decision. But if you have a true null hypothesis and you reject it, that is a type 1. So now let's picture a jury deciding the fate of an accused criminal. He's either guilty or not guilty, in truth. Now they can also declare him guilty or not guilty. And are they always correct when the jury comes to their conclusion? No. Okay. What significance level do they use for all courtroom tests? It's 0.05. Usually, since that's what's accepted by the Supreme Court, that's what most of the courts will go by. Which means that they're saying that their probability of making a type 1 error is only 5%. Okay, so the state of nature is that the guy can be innocent or guilty. And what are your two possible choices that you can make? You can decide he is not guilty, or you can decide that he is guilty. Those are the two verdicts. Okay. So if he's innocent and you declare him not guilty, that is the correct decision. If he's innocent and you declare him guilty, that would be a type. Well, actually we need to back up a little bit. What is the null hypothesis for a jury trial? The null hypothesis is that he is not guilty, and the alternative is guilty. Okay, how do you know that?
Guilty or not guilty.
Okay, because you are innocent until proven guilty. That means that your status quo is you're innocent, and you have to find overwhelming evidence against that null hypothesis before you go with the alternative. Okay, so null hypothesis was correct, that he was innocent, but we decided an error, so that's a type 1. If he is guilty and we decide not guilty, that is type 2. And if he's guilty and we decide that, it is correct. So a type 1 error results in what? If you make a type 1 error, what are you doing to this guy? Okay, so innocent man is guilty. Declared guilty. And if you declare him guilty, somehow he is punished, whether he's off to jail or fines or whatever this case may be. So he was really innocent, but you declare him guilty and punish him. So you could be sending an innocent man to prison. Okay, how do you feel about sending an innocent man to prison? Okay, not pleasant. Well, let's see. In this case, a type 2 error results in a guilty man declared not guilty, and no punishment. So in your mind, which one of these two errors is worse? Okay, and you don't have to have a right answer, like some people will disagree on this. Okay, it's not a statistical question, it's just the ethical question. Would you rather send an innocent man to prison or let the guilty man go free?
Guilty go free.
Okay, so you want to let the guilty go free? Anyone want to argue it with him?
Unless
Unless it's a really guilty person. And it might depend on whether or not you're the innocent person going to prison too. Okay. Because that might change your mind about which one's worse as well. Okay. So a hypothesis test rejects the null hypothesis only if there's strong statistical evidence against it. So remember, that's our status quo, and we need to have extremely strong evidence, or not, well, extremely strong, but we need to have pretty strong evidence against it before we're going to reject it and go for the alternative hypothesis. And it's similar to the legal system because when we declare someone guilty or we reject their innocence, only if the evidence of guilt is beyond reasonable doubt. Okay. Now this next part is truly just due to convention, and honestly your textbook doesn't even follow it, but it's mainstream enough that this is what I'm going to try and say throughout the rest of the class. Okay? So due to convention, if our evidence isn't strong enough to convince us to reject the null hypothesis, we do not say that we accept the null hypothesis. Okay? And this is the whole thing of we haven't really shown that the null hypothesis is true, we just didn't find enough evidence against it. And so keeping in that spirit, we don't like to say that we accept the null hypothesis, we prefer to say that we fail to reject the null hypothesis. Or we don't have sufficient evidence to reject the null hypothesis. So that's what we prefer to say, just because remembering that millions of supporting examples don't prove that something is true. Just kind of keeping in that same vein. That's why in this class you'll have noticed that I was trying to avoid the word accept and trying to say more of the we fail to reject. Okay. Some people aren't as picky about that. Some professors are really picky that you say we fail to reject. But it is more mainstream to say we failed to reject, and that's what I'm going to try and stick with throughout this class. So, again, that's just like the legal system. If we don't have enough evidence to prove that he's guilty beyond a reasonable doubt, what's the verdict? They don't stand up and say innocent, they stand up and say not guilty. They just didn't have enough to show that he was guilty. They didn't show that they established he is innocent. Now, of course, you have probabilities of errors. So, of course, you want to have both errors as small as you can get. Okay. Remember that the probability of your type 1 error is equal to your significance level alpha. So, we're going to set alpha to be some small value before we do our experiment. Okay. Setting alpha small means that there's only a small chance of rejecting the null hypothesis when it's true. Okay, which means that we're requiring strong evidence against the null hypothesis before we reject it. And we're usually going to choose between 0.05 and 0.01. So my question to you is, why don't you just set it to be really small? Like, why not 0.01 or 0.00001? Why wouldn't you set your type 1 error to be that small? What do you think? Okay, so let's put it back in context of our jury decision. So, if we make it extremely hard to make a type 1 error to send an innocent man to prison, then what's going to happen? So if we set that probability of type 1 error really, really small, a lot of guilty men go free. So when you think about it, if you make it really hard to convict someone, then a lot of guilty people go free. So if you make it really hard to reject a true null hypothesis, you're just making it really hard to reject the null hypothesis, which means that you're also not going to fail, or you're not going to reject it when it should be rejected. So the reason that we don't just set our type 1 error, the probability of our type 1 error alpha, as small as possible is that if you increase a type 1 error, or decrease. So if you decrease the probability of a type 1 error, then the probability of a type 2 error increases. And vice versa. Okay, so if you want to try and make the probability of a type 2 error really small, then the probability of your type 1 error would have to go up. Okay. So it's kind of this balancing act. We want the probability of our type 1 error to be small, but we don't want to make it so small that the probability of our type 2 error is huge. Okay. And so for every situation, you have to kind of try and decide, well, what error do I dislike the most? Like, do I want to make sure I don't make a type 1, or do I want to make sure that I don't make a type 2? And it will depend on your situation and the context. Okay? So for this thing, just what type of error do you think is worse? I want you to go home and read through this section at home. Okay? And I'll explain it. So we're going to skip to power. So the power of a statistical test is the probability of rejecting a false null hypothesis. So if you have a false null hypothesis, you want to reject it. Okay? So power is a good thing. You want to reject a false null hypothesis. So you want to make your power as high as possible. Now you will notice that the power is 1 minus the probability of a type 2. Because remember, a type 2 error is the probability of failing to reject a false null hypothesis. So the power, the probability of rejecting a false null hypothesis, would be 1 minus that probability of a type 2 error. So the smaller probability of a type 2 error leads to greater power. And again, all you need to take out of the section is that power is a good thing and you want high power. So how can we increase power and decrease the probability of errors? Because we know that we can't just set the probability of one error really, really small, because then the probability of the next error, other type of error, goes up. So how can you make both probabilities go smaller at the same time? So if you want to make the probability for each type of error be smaller at the same time, you increase the sample size. Now remember, if you do increase the sample size, you might get results that are statistically significant or statistically accurate. It just might not be practically significant. Or you can also decrease the standard deviation of the data, but that is usually out of your control. So for example, if I was measuring the heights of everyone on campus, I'm not really allowed to change the heights of the people in my sample to make a smaller standard deviation. That would be considered a pretty bad thing. So just remember, if you want to make your results more precise and more accurate, increase your sample size. Okay. So, any questions to here? Then the moment I know you've been anxiously waiting, we're going to use a one-sample t-test for our population mean. So remember, what was the difference between a z confidence interval and a t confidence interval? It was whether you knew the population standard deviation sigma or whether you knew the sample standard deviation s. So it's the same thing for a hypothesis test. So we use a one-sample t-test for population mean. Okay, this is for the population standard deviation unknown. So we use it if we want to know the value of your population mean mu, but we don't know the population standard deviation sigma. We have to estimate it with a sample standard deviation s. Okay, and when you think about it, that makes sense. If you don't know the population mean, you probably don't know the population standard deviation either. So a t-test is what you're almost always going to be doing in practice. The assumptions for this test is that your population is normally distributed or your sample size is at least 30. The null hypothesis remains the same, so like our mean equals 160 or our mean equals 40, etc. The test statistic is x bar minus mu naught over s over the square root of n. So that's the only thing that changes, is you put in your s instead of sigma, but once you do it, now it is a t test statistic instead of a z. And anytime you work with the t distribution, you need degrees of freedom. And in this situation, our degrees of freedom are n minus 1. And then there are formulas you can memorize in the book about how you find the p-value for each alternative hypothesis. But we're just going to remember that the p-value is the area in the tails. Okay. So if I'm looking for a mu is greater than mu naught, okay? So mu is greater than, which tail am I interested in? Right tail. Okay. If it's a mu is less than, I'm interested in the left tail. And if it's a mu not equal to, I'm interested in both tails. So let's try an example. A bank wants to know if their mean debt to equity ratio is less than 1.5. They want to make sure that they don't commit a type 1 error, so they make alpha equal to 0.01. So this is a situation where they didn't necessarily care about the type 2 error so much, they just really didn't want to make a type 1 error. So that's a good reason is that alpha to be smaller. They found a sample of 15 of their commercial accounts. The debt to equity ratio for the accounts is as such. So conduct a hypothesis test and report your conclusions. Okay. So one of the first things that we do is pick our significance level, and they told me to use 0.01. Then we also need to check our assumptions. Or some students said I should start calling them requirements instead. So the requirements to do this test is that it is normal or a sample size of at least 30. Okay, so when you look at these plots, okay, how do you feel about the normality? Pretty good, right? This is a fairly straight line, fairly bell-shaped, mostly symmetrical. So I think it is fairly normal. So we're good to go here. Remember, we said the t-distribution is pretty robust. As long as it's definitely not normal, you're good to go. Let's see, I need my null and alternative hypotheses. So my null hypothesis would be that my population mean is equal to what? 1.5, because they wanted to show that it is less than 1.5. Let's go ahead. So this table tells us all of our descriptive statistics, our numerical descriptions. So let's write down they tell us. So the count, that is my sample size, n. So n equals 15. My mean, that's going to be my sample mean, is 1.3433. And sample standard deviation, that's s, so s is 0.1921. What else do I need to do a hypothesis test? I need my t-value, so x bar minus mu naught over s over the square root of n. So let's see, 1.3433 minus my hypothesized value of 1.5 over 0.1921 over the square root of n. I got negative 3.16. Everyone else? Okay. Now, to use the t-table, we also know that we'll need to know degrees of freedom, which is n minus 1, so in our case, 15 minus 1 gives me 14. You'll need to find the p-value. My test statistic is negative 3.16. Look at the alternative hypothesis. Mu is less than 1.5. Which tail was I interested in? I wanted the area in the left tail. So now we have to go try and find the probability that we get a t-test statistic less than 3.16. Now, if you look at the t-table, it only gives you areas in the right tail, okay, and only for positive t-values. How can I rearrange this table to get what I need? Or how can I think about it to get what I need?
Symmetry.
Use a symmetry. So the probability that t is less than negative 3.16 is equal to the probability that t is greater than positive 3.16. So remember the symmetry. So what I'm going to do is I come to my t-table, and I have 14 degrees of freedom. So 14 degrees of freedom, that's the only row that I care about. And I am looking for my, so remember this is set up different than the normal table. So degrees of freedom down the side and across the top is the actual probabilities. And in the middle is your t-values. So I'm looking for my t-value of 3.16, right? 3.16? Okay. So where's 3.16 going to be? Somewhere right here. Okay. So 3.16 is between these two t-values. So what is the area in that tail? The area in that tail is between these two probabilities. Okay. Now, in this situation, the best that I can say is that the area in that tail is between 0.005 and 0.001. So the best that I can say about my p-value is that my p-value is between 0.005 and 0.01. That's the best you can do without getting out an applet. If you want to go online and just search for t-calculator, you can find things pretty easily. Or if you know how to use your calculator to find t-probabilities, you can do that too. But this is the best that you can do using the table. Okay, so that p-value of between 0.05 and 0.001, is that bigger or smaller than alpha equals 0.05? Smaller. So my p-value between 0.005 and 0.001 is smaller than alpha. So if we have a small p-value, we get to reject the null hypothesis. And we can say something like, we have very strong evidence that the, what is it, mean, was it debt to equity ratio? So the mean debt to equity ratio of all accounts, so to change it to your population, is what? So we rejected the null hypothesis, so we have very strong evidence that the mean is less than 1.5. Now again, statistically significant means we're very sure that we were correct here, that we made the correct decision. You might have to ask your boss about whether switching from like 1.5 to 1.34 is really practical or not to him, but you're very sure that it is, that the mean is something less than 1.5. Okay, so that's an entire t-test from start to finish. Questions on that? So we can do our next example. Okay. So we had a Valentine's candy case. I think we actually skipped this problem in here. Okay, assume that we don't know the population standard deviation. Instead, we took a sample of 100 stores, and we found a sample mean of x bar equals 326, and a sample standard deviation of 39.1. We want to conduct a hypothesis test to see if the mean boxes of candy ordered per store will be different from 330. So is mu different from 330? Okay, so that's our question of interest. That's what we want to figure out. So what are some of the steps that I need for this hypothesis test? Okay, normal or large sample size. Okay, which one of those is met? Large sample size. Okay. Let's see. What else do I need? I don't know alpha yet. We need an alpha. Pick an alpha for me. No reason to do anything different. Let's just go with 0.05. And then I need my null and alternative hypotheses. So I already know that what I want to show is I want to know is my mean different from 330. So what would the null hypothesis be? That my mean equals 330. What's next? We need our test statistic. So let's plug everything in. So x bar is 326 minus our 330 over 39.1 over the square root of 100. So negative 1.02. What else do I need anytime I'm working with the t-distribution? Degrees of freedom. N minus 1, so n is 100. Okay. And for my p-value, let's see, my test statistic is negative 1.02. Look at your alternative hypothesis. Which tail am I interested in? Both tails. Now, due to symmetry, the area in the right tail should be equal to the area in the left tail. So I can find one of those areas and times them by 2. So 2 times the probability that t is greater than 1.02. Because the t-table gives me areas to the right, so that's the one that's easy to find here. So when I go to my t-table, I'm looking for 99 degrees of freedom now. And are you going to find it on this table? No. Okay. When we had our confidence intervals, what did we do when our degrees of freedom weren't on the table? We rounded down to be conservative. We're going to do the same thing here. So round down degrees of freedom. what rounding down will do will actually make those probabilities a little bit bigger, so your p-values aren't, so your p-values get a little bit bigger, and the reason we want to make them bigger is we don't want to tell people that we found more evidence than we really did. Because remember, our status quo is we assume that our null hypothesis is true unless we have overwhelming evidence against it. And so you don't want to tell someone that you have more evidence than you really do, because that would be lying. So we err on the side that kind of hurts us. So we just kind of say we don't have as much evidence as we might, just so that we're not overstating our case. So we will have to round to 60 degrees of freedom. That's my next lowest. So 1.02, 60 degrees of freedom. I'm looking for 1.02. So where does that fall? Somewhere over here to the left. So let's scroll up so I can see what that probability is. So that probability is somewhere right here. So what can you tell me about that probability? Okay. So someone said less, but if we look at the probabilities, we had smaller, not as small, not as small, a little bit bigger, a little bit bigger, a little bit bigger, a little bit bigger. So it's actually going to be bigger than, let's see, bigger than 0.10. So this tail is bigger than 0.10, and this tail is bigger than 0.10. So what is my total area? Okay, my total area is bigger than 0.20. So this is 2 times my one area of bigger than 0.10. So it's going to be bigger than 0.20. If you want to know exactly how big, you have to break out a computer or a calculator that's capable of telling you those probabilities. Okay. As far as homework, you are welcome to use any calculator, because on the test you can use any calculator. You are welcome to use an Apple online if it helps you figure things out, but I would make sure on every problem you try and use the table as well, because on the test all you'll have is your table or your calculator, so don't get dependent on an applet or anything on the computer. Okay. So that p-value, even though I don't know exactly what that p-value is, I know it's bigger than 0.20. So how does that compare to my significance level of 0.05? It's going to be a lot bigger. This is a big p-value, and big p-values mean that I will do what to my null hypothesis? Fail to reject. Okay, and what this means is I might have found a little evidence against my null hypothesis, but I didn't actually find enough evidence to reject my null hypothesis. So I would try and phrase it in terms like that. So we didn't find enough evidence to decide that the population mean is different from, let's see. So I was trying to find evidence against the null hypothesis and for the alternative that mu is not equal to 330. So in this case, I didn't find enough evidence to reject this, so I didn't actually find enough evidence to conclude that it is not 330. So how do you feel about the t-test? They're the same as the z-test, right? And these steps of this hypothesis test, and we're going to do them over and over and over again throughout the rest of the semester until you're really sick and tired of these steps. Okay. So now remember, I did tell you this once, but I just kind of keep trying to throw these things in there, because I know we went over a lot of things the first day. So remember, you need to choose whether you want a one-sided or two-sided alternative hypothesis before you look at the data. Okay? Even so, like when I looked at this one and I said, I just want to see if the mean is different from 330, looking at the sample mean of 326, which direction do you suspect it might go? I might suspect that maybe it is less than 330. Okay, but remember we've said that you need to set up your null and alternative hypotheses before you do your hypothesis test. Okay, you also need to pick your significance level before you do your hypothesis test. Okay, and because you might start out really not knowing which way it might go, and so you need to pick it beforehand. And then if you figure out maybe which way you want it to go, you could do the analysis again with a new data sample with maybe a one-sided alternative. Okay, so I want to see if the mean height of everyone on campus is different from 5'10" or 70 inches. So I took a sample of 25 imaginary people, and here are their made-up heights. Okay. We want to conduct an appropriate hypothesis test with alpha equals 0.05. So notice once again they gave me, I gave you the megastat output. So the count, that's your n. The mean, that's your x bar of 66.92. And sample standard deviation, S, equals 3.84. Remember, your sample variance is just standard deviation squared. So if you square 3.84, you should get back to 14.74. So what do I need to do for this hypothesis test? Actually, all of you have should have a t-table and a calculator. So go ahead and try this one on your own, and then I'll write it up here, and then we'll see if you got the same thing as me and if you interpret it correctly. Looks like a fair amount of you are done. So, looks like my plot, it looked like a fairly straight line, so fairly normal. My test statistic is negative 4.01. My degrees of freedom were 24, and I found that I decided, because it was a not equal to, my null hypothesis was, or alternative was that mu is not equal to 70, I needed both tails, and the probability in just one tail was less than 0.0005. So when I double that, all that means is that it's less than 0.001. It might still be a much smaller than that, but all I know from this table is that it is less than 0.001, which is a small p-value, so I rejected the null hypothesis. And because my p-value is less than 0.01, that means extremely strong. So we found extremely strong evidence that the mean heights of everyone on campus is different from 70 inches. I still don't know what it is. I can just tell you that it is not 70 inches. Okay, so are there any parts on that process that are giving you trouble? Now, on my own time, looked at this, and I found a 95% confidence interval for the population mean height to be 65.3 to 68.5. Okay, now what does the confidence interval tell us? You remember these interpretations, so this is a good review for the test. I would have said something like, I am 95% confident that the mean height of all students on campus, since it's my population mean and I want to make sure that myself as the teacher can recognize that when I grade your test. So the mean height of all students on campus is between 65.3 and 68.5. Okay. So basically, we're 95% confident that it's between 65.3 and 68.5. Based on that confidence interval alone, how would you have felt about my null hypothesis that my population mean is 70? That is probably wrong. So, mu equals 70 is not a plausible value at my 95% confidence level, because 70 is not in that confidence interval. So I could reject the null hypothesis that mu equals 70 at, let's see, 1 minus 95%, so 5% significance level. So we're not really going to focus on it much in here, but confidence intervals actually tell us the same things as hypothesis tests. One way to do a hypothesis test is just to check and see, well, was my null hypothesized value is 70 in my confidence interval? If yes, then that's a plausible value, and we have no reason to reject our null hypothesis. But if your hypothesized value 70 is not in your interval, then it's not a plausible value, and I would reject my null hypothesis. Okay. So confidence intervals and hypothesis test gives the same results. So you can use a two-sided confidence interval for mu is not equal to mu naught, or appropriate one-sided confidence intervals for a greater than or less than alternative hypothesis. You just need to make sure that if you want alpha to be 0.05, you use a 95% confidence level. If you want alpha to be 0.01, you use a 99% confidence level. And that's why with the confidence levels, they were using the symbol alpha, and we didn't really understand it at the time. But it's because it does tie into hypothesis testing. So any questions there? So your boss wants you to run a hypothesis test to see if the mean is less than 87 for a data set with a sample size of 20. You found the normal curve plot below. What are you going to tell your boss? how do you feel about that normal curve plot? Is this data set normal? If I look at it, that is definitely not close to a straight line. So this is definitely not normal. Okay, and we have a small sample size. So we didn't meet either one of the possible requirements, so can you do this test? Okay, you can't, so you can't do a z, or not a z-test, but a t-test. Okay, you would have to use a non-parametric test. Again, we don't have time to cover those in this class, but you could go look them up if you ever had to. Okay. So any questions on that one?